people wanted to move the quiz either, I guess, to Monday. And I don't really care when the quiz is. I'll let you vote on it in 1 second. But it doesn't matter. And by the way, not this week, next week, Thursday and Friday, we have off. So there won't be a quiz the following Friday. Okay. So, I'm just trying to do this as fair as possible. Where'd my markers go? So here's what I'm going to do, because this is the only fair way. Why don't you get up? You're going to count. She's trying to get her quiz. If you want the quiz this Friday, raise one hand. Only count only one time. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did you get 10?
Something like that, yeah. Pretty close.
Something like that? All right, if you want it on Monday, raise your hand. I don't think there's an issue.
Fair enough.
Look, I try to be fair, all right? Now, hear me on this one. I just want to make sure I'm clear about this. We're going to be covering power. Power is not difficult if you keep up with it. It's just like the complex number stuff. I didn't look at the average on this quiz, but I think it was higher than any of the prior quizzes. There are a whole bunch of high grades, lots and lots of 10s. So I'm going to say this. If you don't know how to do complex numbers and understand that, learn now, because it's going to be critical. Did you have a question, sir? What? When are the grades what?
On this quiz, when are they doing it?
As soon, when I'm done today, I'm going to go. I got to get to a different computer. I have one at home that works. I don't know why I have all these problems, but there's all these updates that they keep doing. And the computer upstairs I was using just now, I haven't updated it in a week or two. And I don't know if you guys have that same problem, but it's like a cajillion little things that they make me do in this two-factor. I can't do anything, literally, without two-factor, this duo. Did you guys get that or not? It's starting to drive me mad. One time is fine, but every single thing I'm doing, I keep on doing. All right, so they're going around. Now, I'm going to cover power. This is chapter 5, and I'm going to try to tell you the bottom line on this stuff, but I need your attention. This is not stuff you want to blow off. It will come back to really hurt you. So please, I'm going to try to make it clear and simple. And remember, the only thing you saw last time with everything we did and all the other stuff was that you had complex resistances or impedances. That was the only difference. And that was the bottom line. Y'all with me? So with that in mind, I'm going to try to show you what power is in terms of the instantaneous and the average power. The average power is the one we want. So in general, if you have a voltage source, now this is chapter, we're going to skip the one on filters, so it's chapter 6, I think, in your book. Anybody have your books here? Check and see. Chapter 6 is on power, I believe, in your book. This is the thing. So with power, right here, they assume, first, you got to get an idea. We're talking about power related to continuous or a constant frequency of excitation. In other words, 60 hertz kind of thing. Follow me? It's not transient, instantaneous. It's at a constant frequency. Here we're going to have some V of t, a voltage, and that's going to have a magnitude V of m, and it's going to have a cosine of omega t. Now, they're going to put a phase angle in here. I don't like that. I usually make the phase angle 0. They're just saying they're trying to be complete. It's a continuous cosine wave. It never started, never stopped. It's been on forever. That's the way you think it. Then we're going to have a circuit over here, and this circuit is going to have some impedance. It really doesn't matter what this is at this point, just Z. I could show you an inductor, capacitor, resistor, but it's of no point. Now, this impedance is going to do something. It's going to limit the current here. And this current I of t has to have the same time domain form as this, except a phase angle difference. If you excite any linear time invariant system with a cosine of omega t excitation, the response has to be a cosine of omega t excitation with some phase adjustment. You all follow me on this? It has to, for a linear time invariant system. So I of t here, they're going to say is equal to some Im. Another cosine here, it will have the same omega t, but there'll be a different phase angle. And he's calling that theta I. Can you read this in the far back, by the way? Or do I need to write there? Can you see it? Far back. You good back there? This is cosine of omega t plus theta I. It's just the I'm sorry, I'll try to write bigger. You know, if you really wanted to do me a favor, you'd move up, but I'm not gonna make anybody move. I've learned my lesson. There's some people who are very particular about their system. Anyway, that's, y'all with me on this? Now, here's the definition of power. Remember before, what was power when we had just DC current and voltage? What was it always? It was V times I. Do you remember that? Or for a resistor, I squared over I squared times R, or V squared R over R for simple resistors. How many remember that, basically, right? The units would be watts. Now, when we talk about instantaneous power, and this is P of T, this is instantaneous power. It's the power at a single instant in time. It's equal to simply V of t times I of t, as it was before. Now it's a function of time. Remember before it was just V times I? Now I is a function of time. And so is V. Now, when you put these two forms, the time domain form, you're going to get some Vm, Im. These are scalar values. They have only magnitude. Then you're going to get a cosine of omega t plus the phase angle of the voltage times the cosine of omega t plus the phase angle of the current. Now the units of this are watts. But you can see that this can have a whole range of values if it goes over a full cycle or 360 degrees change. It can have a peak value, it can go to 0, and it can have a negative maximum too. This is the instantaneous form. What we usually do is this. We don't care about the instantaneous form, to be frank about it. We care about the average power dissipated or average power associated with any element or circuit. So the average power, the symbol is this, and this is average power. Well, that's the power, average power over one cycle. You know a cosine or sine waveform has 360 degrees or what, 2 pi radians of extent. That would be the period. Is everybody familiar with that concept, right? So if you're doing this, the average power would be the average value of this. It's 1 over t, the integral from 0 to t of the instantaneous power dt. Now that should make perfect sense to you. When we talk about an average value of anything, you simply integrate that anything over the horizontal axis, whatever it is, and divide by the actual distance that you integrated over. How many understand? That's the simplest explanation of average I can think of. Well, if we go ahead and put this in here, we're going to have to do one thing in order to make this integration meaningful. I'm going to have to break this cosine up into 2 parts. Now, most of you, I remember trig identities used to drive me bananas. If you want any trig identity, the best thing to do is use Euler's identity for the cosine of sine. How many remember what Euler's identity is? You do. Some people don't want to admit it. They like to get booed. But in other words, I'm not going to do it here. If you take this cosine, cosine is e to the j argument, whatever it is, theta, plus e to the minus j, that argument divided by 2. How many of you kind of remember that? You all remember that? Take that, and if you, I'm not going to do it here, but if you do it here, and just remember, a lot of you guys are going to have to do this stuff when you get in your senior level courses. I'm giving you a tip. You can memorize all the cosine and sine and tan identities you want, but they'll drive you a little batty sometimes. But if you just replace that with e to the j of, and here it would be omega t plus theta v plus minus e to the minus j of that over 2, and do the same thing here, and you multiply the thing out, you'll see something magical happens. You can easily pull out 2 values, and this whole thing will become Vm Im, and then you're going to get 1/2, and then you're going to get the cosine of simply theta v minus theta I plus cosine of 2 omega t, and this is going to be plus theta v plus theta I. Now some of you are wondering, well, how did you know that? Well, I've done it many, many times, and this is called the sum difference angle. If you have a cosine A, or say cosine A plus B, cosine of A plus C, and hold it, I'm sorry. Let me do it this way, because I'm going to confuse you. Cosine of A, cosine of B is equal to 1/2, and here it should be cosine of A minus B plus cosine of A plus B as such. How many remember that sort of? I mean, you have to have seen it tons of times in your classes. I mean, honestly, I don't know this for a fact, but I mean, by the time I got through my sophomore year, with physics and math, we had cajillions of these identities we had to memorize, especially for calculus. You're always doing these things, right? To get the integration form that was somewhat easy to do. All right, now with that in mind, if you take this as A, that is B, and you go ahead and do the expansion, you get this. Vm Im over 2. And here you're going to get cosine of theta v minus theta I, and it's going to be plus cosine of 2 omega t plus theta v plus theta I. Now, I'm not going to have you worry about this formula. I'm just doing this for completeness. You with me? You're going to see something in a second that will help you understand why that's important to see. You're going to see this term is the only term you care about. You'll notice this term is not a function of time. It's just a function of the angular difference between the current and voltage. Do you all see this, class? Something else I want you to note here. This is a cosine waveform. Well, do you remember that cosine's an even function, and the cosine of x is the same thing as cosine of minus x? How many remember that? It's an even function, right? If it's an even function, it doesn't matter if theta v minus theta I is in that form, or if it's theta I minus theta v. It's simply the magnitude of the difference. Does everybody follow me on this? It doesn't matter if it's a minus or plus argument inside that cosine. With sine, it would. Well, the reason I did this is because if I take that right here, now listen to me carefully. I'm going to integrate that over a period, over 1t, or over a time in which the entire signal repeats itself at least once, possibly twice. Do y'all follow me? And before I say more about this, I have a question for you here. If you think about a cosine waveform or a sine waveform over a period, so a cosine waveform would look like this. Call this just Vm here, right? And this would be a period. Y'all agree with that? I'm trying to just give you a picture. Y'all with me? What happens if I integrate this over a period? Anyone? Tell me the value. Just look at it. Well, this area is this area. You give me that in terms of its magnitude. How many see that? What about this area? Same exact magnitude as the upper part, only in negative sense. How many see that? In other words, the answer is 0 for the integration. That's my point. Now, when you look over here, and I'm about to show you this, I'm going to take this and put it down here and do the integration. But I'll tell you the answer. This part integrated with respect to time, see that 2 omega t? There will be 2 periods that we actually cover with 2 omega t over one technical period. It will repeat itself twice. This will go to 0. That's the kicker on this one. So when I do this integration, I just get to cut to the chase on here. When we go ahead and do this integration, we're going to integrate. I'll put it down one time and only one time, and you get to the bottom line of this. We're going to have 1 over t, an integral from 0 to t of Vm Im over 2 cosine of theta, either theta v minus theta I or theta I minus theta v dt. And the second part of that integration will go to 0. So when I do this, this will go to 0 because it's over an even number of periods. Do you all follow me in this? If you do, raise your hands. I'm just trying to cut to the chase. So you forget about that. And in doing so, the thing you take from this is, and you don't have to flip out on this, when I do this integration, I want you to see this. This is a constant, right? Cosine of theta v minus theta I. How many see that? It's a constant. You can take that, all this stuff out in front. If I integrate dt, I get t evaluated from 0 to capital T. It's capital T divided by capital T is 1. And the bottom line on this is the average power is simply Vm Im over 2 times the cosine of the angular difference between the source current and source voltage. And that's it. And that would be in watts. That is the bottom line. Now, here's one thing you have to take from it, and I need you to be attentive here. Anytime we have a resistor, and I'm going to get to the reason, I'm going to do some problems. Whenever you have a resistor, only a resistor, and let me try to draw this so you can appreciate what I'm talking about. By the way, have you had laboratories with peak power with like engines, like either electrical motors or gas engines or anything like that? Do you get horsepower torque curves or anything? Have you had that? You've had that? Which class? Say again? Oh, well, no, I'm talking about class. No, he's into a specialty thing. All right, well, you're going to at some point get things like this, and they will be talking about the peak power output of an engine, and they'll be talking about the average or the power output that you can sustain without burning the whole thing up. They're two different things. Quite different, as a matter of fact. I don't know if you've gotten into that, but you're gonna find that this is real important when you're dealing with any kind of vehicle. You can get a whole lot of power out for a very short time, especially with electric motors, but you can't sustain it, they'll burn out. Frankly, they'll just blow up in some cases. All right, now with that, I'm gonna just show you some examples of this. Remember, he had average power, and this is the kicker, is 1/2 Im Vm cosine of the angle theta V minus theta I in watts. Remember that, right? Now we're going to talk about what happens for 3 elements. The first is a resistor. So I'm going to make it real simple. I put a voltage here, and I want you to be attentive here. I'm going to put a voltage here, and the voltage is just going to be equal to V. No, I'm going to put hard values. It seems to work better. 10 volts cosine of 377 T volts. This is going to be my voltage, V of T, right here. And I'm going to put a resistor here. And I'm going to make that resistance equal to 10 ohms. I'm making it as simple as possible. With me? Concrete values. I got a voltage of 10 volts at 377 T. Right? Now, how do you solve that problem if you wanted the time domain current? This is a question. So I want the time domain current, but I really don't. I'm just asking it right now. How would you do that? People, how many know? I'm not going to ask you how many know. 1, 2, 3, 4. Okay, quite a few. You're sheepishly raising your hand. I'm not going to call you because I know there's a whole lot of people who don't call it. Okay? I don't like you for starters, and I really don't like you calling me. I understand. All right. Come over here. We go right to the frequency domain. 10. There's no angle, right? You all agree with that? So I'm going to do it over here. Years ago, I did things that I thought would make the class a little more interesting and fun. I'd call on somebody and they got to call on the next person. Almost had a fist fight. People don't like to be called on, especially by people they don't like. All right. So down here, if we go to the frequency domain, we get 10 volts at 0 degrees. Does everybody agree with that, first of all? How many understand that? See it in the back? Now, that's the voltage. The resistance here is still 10 ohms. So I need the phasor current, right? What's that phasor current going to be? It's pretty easy, I think. I'm going to see it. I'm not going to call on you. Anybody want to tell me? I'm going to see it's 1 amp. 10 volts by 10 ohms, 1 amp, right? What's the angle? It's 0, right? If there ain't an angle, it's 0. Do y'all follow me, class? No angle is a 0. It's 0 degrees, so it's 1 at 0 degrees. All right, now, take a look at the average power for this. The average power dissipated by that resistance. Resistors dissipate power. Do y'all follow me? It would be what? 1/2 the voltage, 10, times the current, 1, right? Times cosine of, which is, everybody see it's 5 watts? That's 5 watts. You all with me? Something I haven't said is this value 10 will be termed the peak value of voltage. You're going to see there's something called the RMS, or root mean squared value, too, later. Some of you have heard these terms before and for other reasons, but I'll get to that. I'm just trying to show you how simple it is. Now, the resistor, obviously, has an average power that it will dissipate. Now I'm going to do the same problem, but I'm going to put an inductor. You all with me? And you're going to see we don't need this over and over again. The only thing we need is the angle here. You all with me? And the angle of the current. The difference in those two angles is what goes right there. You all with me, class? That's it. So over here, let me just do this with an inductor over here. Make it easy. This is going to simplify a whole lot in a little bit, but right now I got to get through the basics. So if I have that 10-volt source as before, still an angle of 0 degrees volts, but now I'm going to put an inductor on here. An inductor has an impedance of J10 ohms. And I want this phasor current. Can everybody follow me? Same exact form as before, only now we have a complex impedance. Y'all with me? All right, what is the value of that current? By definition, it's always going to be V over the impedance, right? So it's V, or 10, at an angle of 0 degrees. If it's 0 degrees, you don't have to put it down. Divided by J10. You all agree with that? I made sure I wrote everything out so there's nothing left to chance here as far as your understanding. Now 10 over 10 is 1. But what is 1 over J? Anybody? Minus J. Do you agree with that, class? How many do? Sure. It's minus J. Well, minus J can be expressed in terms of a polar form as a magnitude of 1 at an angle of minus 90 degrees. How many see this? Far back, can you guys? I always worry about the people in the back. I don't know how in the world, but you somehow can manage to see this stuff. Y'all with me on this one? All right. Now, what's the average power dissipated by this? And by now, I think you can see it. Well, average power would be technically, it's the magnitude V times the magnitude I, which is 1, times the cosine of theta V. Well, theta V is 0 minus the cosine there, or plus 90 degrees. So what is the cosine of 90 degrees, or the cosine of minus 90? Anyone? How many see it's 0? 0 watts of average power. This is 0 watts of average power. And the reason is there's a 90-degree difference between the current and voltage. You will find that the average power absorbed by any inductor is 0, always. Average power. You with me? It can store energy. That would be an instantaneous power that would be being absorbed. Then it can dissipate that energy. But the average amount of power dissipated is 0. Now, what do you think would happen, just a guess now, if I put a capacitor there with minus J10 ohms? Anybody want to guess, not at the current or voltage, but at the average power dissipated? Anyone? Why? You're right. You know the current and voltage through that will have a 90 degrees phase shift because of that J. You all see that, class? How many do? That will always, and I say this again, always be the case. Average power absorbed by a resistor, the easiest way to get it, I'll tell you this, is just 1/2 the magnitude of the current through that resistor squared times R. That way you can't mess up. Just find, it's going to be, if it's a cosinusoidal variation, which all these are assuming. For a resistor, it's fine, just 1/2 I squared times R. For an inductor or a capacitor, it's 0. It's that easy. So I want to do a problem that's slightly more complicated, but it'll just showcase this in the best possible way I can think of. And by the way, to get the values of current through resistors, or for that matter, voltage across them, in the circuit, when you have inductors, capacitors, and everything like that, you use all your tools. You can use nodal, mesh, Thevenin, you can do source transforms, you can do superposition, anything your heart desires to get the answer. In other words, there is no one route to the final answer that beats all. I always go Thevenin. If it's a single element I want the thing, that's me personally, it's much easier usually. All right, so what happens now, I'm gonna put a value of voltage, now watch, slightly more complicated. I'm gonna make this 10 at an angle of 30 degrees volts. With me? Now, I'm also gonna come over here. I'm gonna put a resistor here of 10 ohms. And I'm gonna put an inductor here of J10 ohms. And here's a typical quiz problem. So I've got this, and I'm gonna ask for the voltage here. I'm gonna ask for the voltage here. I'll call it VL. And I'm gonna ask for the average power dissipated by that resistor and the average power dissipated by that inductor. Now these are straightforward things. Y'all follow me? Now think for a second, how would you do that based on what you've just seen? Well, most of you probably, I mean, some of you are just gonna say it's a joke. No, I'm just asking this because it's the next logical step to get where I wanna go. I don't wanna make too much information all involved in one step or else you'll miss something. Well, the first thing we need is the current. Do y'all agree with that? The phasor current. We know that, I just told you that will be the key. Isn't that right, class? So, what is that current gonna be? And again, you could use voltage division from voltage, but I want to get the current for one specific reason, to get the power through that resistor. You all with me? I'm trying to show you how I would do it. All right, well, that current will always be the voltage divided by the impedance. Can everybody see there in series here, class? Far back especially. You all see that? All right, so listen, I'll need your help on this one. I have 10 at an angle of 30 degrees divided by 10 plus J10 ohms. Can you give that to me in terms of a magnitude and an angle? Anyone? I can pretty much get it. I got 10 over 10 square root of 2, 30 minus 45, so it's minus 15 degrees. And the magnitude looks like it's going to be 1 over the square root of 2, I believe. Anybody want to confirm that or deny that? You got that? How many got that? Okay? If you don't, get your calculators out. Make sure you can do it. I don't want anybody left wondering. I trust most of you can do this without much effort. Now, that's amps, right? All right. What is the power through that resistor? And I might as well just put this stuff over here so you have it down. Write it in your book or write it in your notes somewhere. All these are the same. This is going to be when you have AC power or voltage sources. That's alternating current, like the wall there, 60 hertz. So when you have this, if you have a single resistor, and this resistor has a current I, and the resistor has a voltage VR across it. I'm just showing you this. What will happen is, and I'll get out of your way, the average power dissipated by that resistor can either be 1/2 magnitude of Im, magnitude of Vm, or 1/2, and this is the part I like, I take magnitude of Im and square it, that's the magnitude, gets rid of the phase angle, times R, or because I times R is V, you can just simply say this is really V squared, and it will be the magnitude, V squared over R divided by 2. Now all of those give the same answer. The one I like is this, me personally. So if you look at that, now just look at it, you'll know, here's what people get hung up on. Well, they see minus 15 degrees and they see 30. And they say somewhere, somehow, I have to use that cosine of 30 minus 15. You don't. You with me? You don't have to do that because we have the current. Do you all see that, class? How many do? You can do it if you want, but you don't have to. Here, this is simply 1/2 magnitude of the current, which is 1 over the square root of 2, squared times the resistance, which is 10. So that's going to be 10, right, divided by 4, or 2.5 watts. Does everybody see that? How many do? Can you see it? Did I mess up? You got a hard look. Let's see. I've got 10, and I got 1/2 squared. Isn't that 1 over 2 times 2? That's 1 over 4 times 10. I think that's 2.3.
Wait, so power equals I times V, and you multiply I squared times V?
I squared times R. Is it? R is 10.
I thought 1 over square root of 2 was I.
Yeah, 1/2 I squared R, right? R is 10.
Am I not crazy? Oh,
Look.
okay, yeah. I didn't see the equation in between.
Sorry. Y'all with me, class? How many are? Yes. Did you have a question?
Yeah, does squiggling it get rid of the phase angle, or do we just give up the magnitude?
That's right. It gets rid of it. That's why I did. I don't want to deal with the phase angles. I hate phase angles if I don't need to use them. I don't want to have a cosine of voltage phase minus current phase if I can possibly forget about it. Now, something else I'm going to tell you. Listen, you can go ahead and you can say, well, the current is that 1 over square root of 2 at an angle of minus 15 degrees. Do you see that? Now we can say this whole thing looks like a single impedance of 10 plus J10. With me? The total voltage across it is this, right? So just listen. So the total power dissipated by the sum of those two could be given, this would be the average power. This would be for both of those elements, would be 10, right, times the magnitude of the current, which is 1 over the square root of 2. I'm just using this formula. Then I have to divide that by 2. You all with me? And then you have to take the cosine of the actual difference in these two, which is theta V minus theta I, which is 45 degrees. And you all see what I've done here? You have to take the difference in the phase angles. One phase angle is 30, or is 15, minus 15 degrees, the other is 30. That's a total difference of 45 degrees. Do you agree with that, class? How many do? You all see it? All right. Now, so I take Vm, 10, times the magnitude of the current, 1 over square root of 2, divided by 2, it's that formula. Then the cosine of the difference, which is 45 degrees. What is cosine of 45 degrees? 1 over square root of 2, right. And this whole thing becomes what? 2.5 watts. Now, what I'm saying is all the power dissipated by these two elements is the resistor. We just calculated the power dissipated by the resistor. We found out it's 2.5 watts. It's also given by this formula, because the total power dissipated by that circuit using this voltage and the actual total current is just the power dissipated by the resistor. Now, the reason I'm sort of stressing the importance of getting current and looking at resistors, that inductor doesn't do anything. If there's a capacitor down here, it doesn't dissipate power. You use those values to get the current, but once you have the current, just 1/2 magnitude of that current squared times that resistance, and that's it. That's all she wrote. Make life simple. You're gonna see some problems in the book, some examples, where they're gonna go ahead and do this way. They're gonna do this crap. They don't need to do that. And I speak to you, somebody that's done this stuff for a long time. Always make things easy so things you don't make less mistakes that way. Okay? Did you have a question?
Yeah, for the resistor, for the P average, where's the cosine 15 in for the current?
Well, wait a second. I think, are you talking about this?
Yeah, and we're doing that formula over there, the P average equals 1/2, 1/√2. Where's the cosine?
Whoa. This right here is simply, this formula I'm showing you has no cosine. It's what? 1/2 the magnitude of the current through the resistor times the resistor. Isn't that the one I put right here, Sid?
Yeah.
That's that one, all right? Now, right here is where I take this voltage source, right? And I've got that current. So I take, that voltage is 10, the current is 1/√2, right?
Yeah.
Then I have to divide by 2, it's right here, right? Then I have to take the cosine of the angular difference. That angle is minus 15, the source was 30. 30 minus 30, there's a 45-degree difference. Do y'all follow me? It's 30 minus a minus 15 or 45 degrees. Y'all with me, class? All right, but they're both the same. My real point is, just get the current. That's the real point. Okay, now, something else. In his book, I want to just make mention of a few things to try to keep you on the right track. I don't want you to get all worked up about just how much trouble it can be to calculate these things. The big thing you're going to see with the problems in this chapter on average, actually, I said there was 6. This is actually chapter 7. I'm sorry about this. So it should be chapter 7 in this text. Or in my text, I'm looking at chapter 6 is on filters. We're skipping the section on filters right now. We'll come back and talk a little bit about specific filters that you'll need, some of you will need. But this is going to be chapter 7. And in chapter 7, we're going to get to RMS in a second. I want to show you one thing to help you. Yeah, I'm going to say one other thing. I didn't say it here, but we did this before. Whenever you have a circuit like this, the total power supplied is equal to the total power dissipated. That should make logical sense to everybody. Are you with me on this, class? Now, I really don't want to spend much time on that. If I have two sources, one could actually be absorbing power. I'm not going to try to trick you on that. The real thing is this. For all these circuits you're going to encounter, you're going to have to be able to get the voltage and currents using the different tools you have available. And then from that, get the average power dissipated by the elements. You with me, class? That's the real thing about this. He's going to show you some problems. The topology looks a little complicated, but you don't have to fret. And he'll also ask about, well, he's gonna ask for the total average power supplied and everything like this. I'm gonna take a look at problem 716, and the reason I'm doing this is just to show you the class of problems he's gonna ask and how to go about doing it. They're not hard at all. But you do have to be careful, and you have to know how to do the complex math and get the right values for the current voltages. All right, so this is problem 716, and I think you should be able to do this just with what I told you fairly easily. He wants the average power supplied by the network. Here's a tip. By the source. This is the voltage source. The only thing this is going to supply some power. The only thing that's going to dissipate power are these two resistors. Do y'all follow me? How many are with me on this? So you can do this any way your heart desires. How do you want to solve that? What am I really after? Let's just answer that question. I would like to get the current here, call it 1, and I'd like to get the current here, call it I2. Do you agree with that, class? How many see if I have those two currents, I can get those two powers? Now that would be the total power supply, because that inductor, average power, that inductor does zip as far as dissipate power. You with me? It does limit the current though. So how are you going to solve it? I'm asking everyone. I'm not going to call on somebody. Anybody want to volunteer some information besides Google it? I had a kid tell me that one time. You can do it how many different ways? How many C you can do with nodal? Yeah, if I ground this, I don't care how you do it. And just call this some unknown value V, right? With me? And then you put the current. Well, I already called that I1. I called that I2. Might as well call this I3. You agree with that? But you want to do it with nodal. And then I got to put a ground that's 0 volts. You don't have to. I don't care how you do it myself, but I'm just showing you. It's one possibility. So now what do I do? Well, now we do Kirchhoff's current law. Whatever flows into this node right here, right, flows out. If you look at what I've written, what flows in? I2. What flows out? I1 and I3. Everybody agree with that? You'll see it. I'm really not trying to bore you, but I think I am. All right. What is I2? Well, the current going that way is this voltage minus V. I'll just write it down quickly. So it's 12 at an angle of 30 degrees minus V over that resistance 2 equal to I1, which is going to be V over 1, right? Or just V, and plus I3, which is going to be V over J1. Now, I know I'm out of time, but how many see this? How many believe they can get the value of V? Once you have V, if you want this current, it's V over 1, or it is V in terms of magnitude. When you want this current, it doesn't matter, does it, class? There's no power. If you get this current, it's going to be 12 at an angle of 30 minus that current. Okay, I'm going to give you some homework problems. I'll see you Friday. Please come.